We're in a lab synthesizing a molecule. We need to have ways to determine if we've actually made that molecule and determine how pure it is. These ways are called analytical techniques. You've used some of them in general chemistry. This semester and next, we'll be using a variety of analytical techniques to help identify what we've made in lab, such as thin layer chromatography, TLC, infrared spectroscopy, IR, nuclear magnetic resonance spectroscopy, NMR, and gas chromatography mass spectroscopy, GC-MS. Over the next few weeks, these techniques will be introduced to you. More time will be spent on IR and NMR in lecture, so don't panic if the assigned reading is overwhelming. Of these 4 techniques, TLC is much simpler than IR, NMR, and GC-MS. Chromatography is a technique used to separate the components of a mixture. As a side note, there are several different types of chromatography that we will encounter in organic chemistry. In addition to thin layer chromatography, there's column chromatography, gas chromatography, GC, and high-performance liquid chromatography, HPLC. Although these are different techniques, the theory behind them is the same. We'll focus on TLC now, and we'll use column chromatography and gas chromatography later this semester and next. TLC is a simple, quick, and inexpensive analytical tool and requires a small amount of sample. TLC is used to check the purity of a compound, determine the number of components in a mixture, monitor the extent of a reaction, and help identify unknowns in a sample by comparing it to known compounds. In most labs that we do, TLC will be used to monitor the extent of the reaction. Did it go to completion? Did product form? Is the product pure? Are starting materials present? In this first lab, we will be learning the technique by determining the identity of an unknown. Let's first review the theory, then demonstrate how this technique is carried out. TLC is based on the distribution of compounds in a mixture between 2 phases, a solid stationary phase and a liquid mobile phase. The mixture is typically dissolved in a solvent. This distribution, or separation, depends on the differences in how strongly components are adsorbed to the stationary phase versus how soluble the components are in the mobile phase. These interactions set up an equilibrium between the 2 phases and the sample components, and is based on the relative polarities of the components in the mixture. In terms of TLC, what are these phases? What is the stationary phase, and what is the mobile phase? The stationary phase is a polar solid, silica gel, that is coated onto a flexible plastic or glass backing. This is referred to as the TLC plate and is roughly 1 inch by 2 inches, small enough to fit into a developing chamber. The hydroxy groups, or OH groups, make the silica gel and thus the TLC plate very polar. Typically, the silica gel is mixed with a fluorescent indicator to help observe the presence of the components. We'll see an example of this in a little bit. The other phase is the mobile phase, which is the solvent that moves up the TLC plate by capillary action. Depending on the component's attraction to the mobile phase versus the stationary phase, some components will move farther up the plate than others. This is based on the functional groups present and the polarity of the components. In general, since the stationary phase is strongly polar, it strongly binds polar components. The mobile phase is less polar than the silica gel and more easily dissolves or attracts the components that are less polar and/or nonpolar. Separation occurs from differences in the amount of interactions the individual components have with these phases. The more polar components have more interactions with the stationary phase and do not move very far up the plate, if it moves at all. The less polar and nonpolar components have more interactions with the mobile phase and move farther up the plate with the solvent. By carefully choosing the polarity of the mobile phase, almost any mixture can be separated. Solvents are shown here by increasing polarity. All of these solvents are available at your lab bench. Again, in general, nonpolar components move up the TLC plate farther than polar components because they have a smaller affinity for the polar stationary phase. However, if too polar a solvent is chosen, all of the components, polar and nonpolar, may simply move up the plate with the solvent with no separation taking place. The best solvent is often found by trial and error. Sometimes a single solvent can be found that will separate all of the components of a mixture, but often a mixture of solvents is necessary to achieve separation. Note that toluene, ethanol, methanol, and water are typically not good solvents to use for the mobile phase. Toluene has a high boiling point and will remain on the TLC plate after development. We will see that organic compounds tend to be UV active and will show up as dark spots on a TLC plate when viewed under UV light. Toluene is also UV active, so if the solvent does not evaporate, the entire plate will appear dark under UV light, obscuring the sample spots. Ethanol, methanol, and water are very polar solvents, and they will be strongly attracted to the silica gel. As a result, the sample components will leave a trail referred to as tailing up the plate. The sample component will be dissolved in the solvent, but since the solvent is attracted to the silica gel, some of the sample will be deposited and left behind on the plate as the solvent moves up the plate. This tailing is also common with components with polar functional groups such as alcohols and carboxylic acids. In terms of specific component functional groups, the more polar groups, like alcohols, amines, and carboxylic acids, will have little movement up the plate because they have a stronger bond to the silica gel. The more nonpolar groups, like hydrocarbons, will move the farthest up the plate because they have a weaker bond to the silica gel. To pull these concepts together, let's look at how TLC is carried out. Before you get started, make sure you have TLC plates, microspotters, a developing chamber with lid, solvents, samples, a graduated cylinder, tweezers, a pencil, a ruler, and a paper towel. In a glass developing chamber with lid, pour approximately 5 ml of the appropriate developing solvent into the jar. Close the lid to prevent solvent evaporation. You should have a layer of solvent no more than 5 to 8 millimeters deep. A sample is applied to the dull side of a plastic-backed silica gel plate using a thin glass spotter or microspotter. Before you apply the sample, it is helpful to mark the plate so that you can keep track of where the sample is applied. Using a pencil, gently draw a straight line approximately 1 centimeter from the bottom of the plate. Don't use a pen, since the ink is soluble in organic solvents and will be developed along with the sample. Make sure you always mark the dull side of the TLC plate, directly onto the silica gel, not on the shiny plastic side. At the end of this video, there is a demonstration on how to cut the TLC plates to an appropriate size. Once you've drawn the horizontal line, which is referred to as the origin, lightly draw small tick marks or dots on the line at each point where you will apply a spot of sample. Be sure to write down what sample you place on each spot to keep track of the samples. The trickiest part of TLC is applying samples to the plate. Some practice will be needed to consistently apply the correct amount of sample. The sample should be fairly dilute, containing roughly 1 to 2% of the sample compound. These will generally be prepared for you. If the sample is too dilute, it would be difficult to see on the plate. However, if it's too concentrated, it will typically streak or tail up the plate after it has been developed in solvent. Spot the plate by dipping the microspotter into the sample. Capillary action will draw the liquid sample up into the micropipette. Apply the sample by gently and quickly touching the micropipette to the TLC plate. Depending on the concentration of the sample, you may need to spot the sample once or twice. Allow the solvent to evaporate between applications and make sure you spot the plate in exactly the same position each time. Remove the spotter from the plate before the sample spot grows to more than 2 millimeters in diameter. The smaller the spot, the better the separation will be. It's difficult to separate mixtures on a TLC plate when the spots are too big. Also remember to use a different microspotter for each different sample. Once you have applied the samples and they have dried, develop the plate by carefully placing the plate in the developing chamber. Use tweezers to do this. Make sure that the sample spots are above the solvent level, otherwise the sample will dissolve into the developing solvent. Place it in the jar evenly and cap the jar to maintain an atmosphere saturated with solvent. Keep a close eye on the solvent front. Do not let the solvent get any closer than 1 to 2 centimeters from the top of the plate. If solvent does get to the top, it appears to stop moving, but the sample keeps moving up the plate. This leads to an incorrect measurement of how far the sample has moved compared to the solvent front. While the plate is developing, let's review. Initially, the components of the sample adsorb to the silica gel particles at the bottom of the TLC plate. As a mobile phase solvent moves up the TLC plate by capillary action, the solvent, or eluent, dissolves the sample, or solute, and displaces it from the silica gel, moving it up the plate. As the solute moves up the plate to fresh silica gel, new equilibria are established between the silica gel sample and solvent. This constant equilibration means that different components will move up the TLC plate different distances depending on their relative affinity for the silica gel versus that of the solvent. When the solvent is 1 to 2 centimeters from the top of the plate, use tweezers to remove the plate from the developing chamber. With a pencil, immediately mark the position of the solvent front, which is the position where the solvent has reached. This will be important for the calculation of RF values. Let the plate dry on a paper towel until the solvent has evaporated. I find that it is easier to pick up the plate from a paper towel rather than from directly on the bench top. When components of the sample are visible to the naked eye, visualizing the movement of the sample after development is easy. However, most organic compounds are colorless and cannot be seen on a TLC plate with the naked eye. Fortunately, most TLC plates contain an indicator that causes fluorescence under UV light. Many UV-active compounds can quench this fluorescence, and as a result, the sample appears as dark spots on the glowing TLC plate. Place the developed TLC plate under the lamp. Turn the switch to short wave. Lightly outline the sample spot with a pencil. Components on the plate will be seen as spots. The retention factor, or RF value, of each spot is used to quantify the relative polarity and is calculated by dividing the distance the sample traveled by the distance the solvent traveled. Distances are measured from the origin, not the bottom of the plate, to the middle of the spot for the sample, to the solvent front for the solvent. Given the same set of conditions, the sample component will have the same RF value. Since polar components do not move very far up the TLC plate, they will have smaller RF values than nonpolar components under the same developing conditions. The following series of TLC plates shows the effects of solvent polarity on RF values. As the polarity of the mobile phase increases, as shown left to right, the sample moves farther up the plate. The value of D sample increases, while D solvent remains constant. Increasing the polarity of the developing solvent generally increases the RF values of all the sample spots. Typically, you want to use a developing solvent that yields RF values between 0.2 and 0.8. This generally results in the most effective separation when you have more than one component in a sample. For example, a mixture containing 2 components was spotted and developed in a nonpolar solvent such as hexanes. The final plate showed only one sample spot with a small RF value, less than 0.2. The solvent is too nonpolar. The same mixture was developed in a more polar solvent, such as methylene chloride. The final plate, again, showed only one sample, but this time with a large RF value. When a mixture of hexanes and methylene chloride was used, 2 sample spots were seen separately. Clearly, the mixture is the better mobile phase. TLC is frequently used to determine the identity of the components of a mixture. Since small deviations in TLC development conditions can affect RF values, comparing the RF values of different samples is usually done on the same TLC plate. If we know that an unknown sample is composed of either compound A, compound B, or a mixture of the two, TLC can be used to determine the identity of the unknown. Using two TLC plates, spot one plate with the unknown on the left, known compound A on the right, and a spot in between the two consisting of both the unknown and compound A. This is known as co-spotting. Repeat this process for known compound B on the second plate. After developing the plates separately, compare the results. Since the co-spot with known compound A shows an additional spot compared to the unknown, this suggests that the unknown does not contain compound A. However, since the co-spot with known compound B shows only one spot compared to the unknown, this suggests that the unknown contains compound B. This same technique can be used for unknown samples with more than two compounds, as long as you have known compounds for each component. You will also need more TLC plates, one for each different component. We have reviewed the basic techniques for thin layer chromatography. You have learned how to prepare a developing chamber and how to choose a solvent, how to prepare the TLC plate by marking in pencil and applying the sample, how to develop the TLC plate in the chamber with the mobile phase, how to visualize the plate with shortwave UV light, and how to calculate RF values. Lastly, you learned how to co-spot in order to identify and verify the components of a mixture. In lab today, you will be identifying the components of an unknown. The possible compounds present are benzyl alcohol, benzaldehyde, and benzoic acid. 1, 2, or all 3 of these may be present. You will have known standards of each of these compounds with which to compare and co-spot. I would suggest first evaluating your unknown sample with all 3 of the unknowns. In other words, 4 samples on a plate. If you do not feel comfortable evaluating all 4 at the same time, first try 2 at a time. This preliminary plate should give you an idea as to which components are present in your unknown. You may be able to eliminate 1 or 2 of the unknowns, but you should verify your conclusions by co-spotting. What solvent should you use for the mobile phase? How about testing the known samples with a polar solvent, such as methylene chloride, then a non-polar solvent, such as hexanes, and then a 50-50 mixture of the two? Look for the solvent or solvent mixture that yields the greatest separation between the 3 sample spots. Typically, you want the RF value difference, or delta RF, between the 2 components to be greater than 0.25. Be sure to read the lab handouts for additional information, and remember that it's important to understand both theory and technique in order to become a good experimentalist. Continue watching to see how TLC plates are cut to an appropriate size and how to prepare microspotters. The TLC plates that we have available are coated with silica gel, which has been mixed with a fluorescent indicator. The backing is plastic. They come in strips of 2 inches by 8 inches, so they need to be cut. 2 inches by 1 inch is a good size and will fit into the mouth of a developing chamber. You can measure this with a ruler or just eyeball approximately 1 inch. Gloves should be worn while handling the plates. It is important that you do not touch the face of the plate with your fingers. Oils from your skin or other contaminants can be absorbed and affect the results. It is best to only hold the plates by the edges or with tweezers. The easiest way to cut the plates is with sharp scissors. Slowly cut the plate to avoid chipping the silica gel. As you can see, some chipping may happen, but if it's not too bad, you can still use the plate. But position the plate so that the chip is at the top where it won't affect the movement of the solvent. Make a handful of these and store them in your drawer in a plastic Ziploc bag. This way you won't need to cut plates in every lab. Sample is applied to the TLC plate using a thin glass spotter or micro spotter. These are commercially available. However, in many laboratories, they are prepared by heating and stretching capillary tubes. A benefit of homemade spotters is that they are usually thinner than commercially available microspotters and deliver smaller amounts of sample. You want to use capillary tubes that are open on both ends. That way you can make 2 spotters from one capillary tube. In the lab, use the capillary tube container marked TLC. The capillary tube containers marked MP are for melting point and are only opened on one end. Turn on a Bunsen burner, ensuring that there are no flammable solvents nearby. Place the center of a capillary tube into the blue part of the flame. Slowly rotate it so that it heats evenly. The flame will turn yellow as this is happening. Once the glass starts to soften, quickly remove the capillary from the flame. Move it up, then pull the ends away from each other to stretch the glass. Up and out. The middle is now much narrower. Bring the ends together to snap the glass in half. The resulting ends are much too narrow, so using a pencil, gently tap the ends so that the glass breaks at the weakest point. Be sure to do this over the glass waste container. You will end up with 2 fine-tipped microspotters. This will take a bit of practice. If the capillary tube isn't hot enough when you pull it, you won't be able to stretch it. If you leave it in the flame for too long, it will turn into a soggy mess. Make a handful of these and store them in your drawer so that you don't have to make spotters every time in lab.
She blinded me with science.